So if you're the type of person who likes to smash things together, do I ever have the program for you? My name is Brian McGuire and I'm here at Science North, and I'm going to simulate what would happen if an asteroid were to collide with the Earth. Now to do this, you can follow along. I'm going to go to a website called Impact Earth. Now you can do a web search for Impact Earth and it should be the first result. But as well, you can have a look at our Cool Science website at www.sciencenorth.ca, and I'll have links there as well. What we're going to simulate today is what would happen if the asteroid U-55, or 2005 U-55, were to strike the Earth. Now on November the 8th, it's set for a close approach, but it's not projected to actually hit the Earth, and it's not any type of danger to us right now. So don't panic about that one. We're just going to do this for fun. To get some of the parameters for U-55, I'm going to have to go to another website. So I'm going to bring up the Solar System Dynamics website, and here I have it loaded up to 2005 U-55. Here's a little diagram that's kind of neat to look at. If I zoom in here on the Earth, you'll see that 2005 U-55 is actually very close to the Earth right now. Here's November 7th, and if I zoom out, you can see the rest of the orbits of the planets. But we're more interested in the parameters, so I'm going to scroll down, and here you can see the diameter. That's one of the parameters that I need to know. It says that it's 0.4 kilometers, so 400 meters. We'll remember that. Another thing that we'd like to know is the velocity. So here we have a relative velocity, so relative to the Earth, and here we have an absolute velocity. You'll see that the two numbers are very close, and in our Impact Earth program, it just wants rounded to the nearest whole number. So we can use either value, and it should be valid in our simulation. If we look over here, there are a bunch of dates. I'm going to go down to 2011, November 8th. And if I scroll over, we can see that the speed here is 13.7, 13.6. So we'll round up to 14. So the speed of the asteroid does change throughout time depending on the different gravitational forces that are acting upon it. We'll go back to Impact Earth. So now we're back here. We can see that we don't have any values yet, but we'll fill some of those in. So our diameter was 400 meters. There we are. And our velocity, we'll go with the knowns right now. Velocity, we'll put that at 14. Now the density, we're not quite sure of yet. We know just about what asteroids are made up of, but we don't know the exact density of this particular asteroid or its composition. As it gets closer to us, though, scientists and astronomers will be looking at it, and hopefully they'll be able to determine that with more accuracy. But for now, we'll have to choose one of these simulations. So it's going to be dense rock, it's going to be iron. Let's go for worst case scenario. Call it iron. There we are. Now the impact angle is also a variable that's very hard to figure out, because as it gets closer to us, we can make small adjustments, but it would have to get quite close to us before we could really determine the impact angle. Looking at this diagram, it also makes the impact angle look like it's a two-dimensional thing. But we have to remember that space is three-dimensional, so as much as I can vary this towards the top of the Earth and the bottom of the Earth, or the north and south, there's also a chance that it might hit to the right or left of the Earth. So we can, if we just put in, we'll go for a 90 degrees. Now 90 degrees is not necessarily worst case scenario. If it hit on a very shallow angle, that might be worst case scenario, because it would actually, it might skip, it might take throw a lot of debris very far. So we'll go 90 degrees. The last parameter that we have to put here is where it's going to hit. So if your area has a lot of sedimentary rock or crystalline rock, you can find that out if you'd like to simulate a hit near your area, or you could go for water. So it might hit water, which would have a very different type of impact than if it hit rock. So let's keep it at rock for now. We'll keep it at sedimentary rock, and if you do put in water, you can put the depth. The last parameter is how far away are you from the impact. If you're right under the impact, then that's unfortunate, but if you're somewhere else, you may be affected by it as well, even all the way around the world. So let's say that this impact happened in and around down south. Well, we're in Sudbury here. Let's say 450 kilometers down south. So unfortunately, in a fairly populated area down in southern Ontario. Now I'm going to calculate the impact by hitting this button right here, and it's going to show me a neat little animation. I hope that's not happening right now. And you can also skip it if you'd like, but it's kind of entertaining the first time. And there we are. Leave the rest to the imagination. And it shows us our inputs here. Make sure everything's good. And it has 9 different sort of variables of the impact, or results of the impact. So if I click on atmospheric entry, it will tell me what will happen as it enters the atmosphere, and we can look through each of these. So I'm not gonna jump through all of them. It will take some time, but you can have a look at these on your own. There is no tsunami data because it didn't actually hit the water, and we also didn't put in data for how far away it would have been from water, which may have also caused a tsunami. But you can see that there's all sorts of different. So aside from the obvious crater, it'll tell you how deep the crater would be and what the diameter of the crater would be. There's also ejecta, so what would be thrown into the atmosphere. Air blast, thermal radiation, seismic effects, and it's saying here that it'll arrive 1.5 minutes later, according to the distance that you put in, the distance from the impact. So 22.7 minutes later, there'll be an air blast. It'll be as loud as heavy traffic. So using all this, you can do a simulation of what would happen if a large object hit the Earth, and I think that's very interesting to check out. And again, U55 is not a danger to us right now, but it's a lot of fun to do this. Join us at www.sciencenorth.ca on our Cool Science website for other neat science facts.